Hello, so we have been looking at sequences and series over the last couple of sessions, and today we're going to do a tiny bit more on these, some of which you may have encountered before or I've mentioned before. So first, an extremely quick recap on sequences and series. So if we first look at sequences, we studied two main types. We studied arithmetic and geometric. Arithmetic, there we go, and geometric. And a sequence is just an ordered list of numbers that we usually write with commas in between. So an example of an arithmetic sequence, we could have this one, 1, 2, 3, 4, and so on. We're literally just adding 1 on each time. Just out of interest, we also call this set of numbers, so the set of whole numbers starting at 1, we call these the counting numbers, or you ought to know this symbol, can't draw it, which is n for the natural numbers. Now there's actually there isn't a consensus over whether 0 is included in this, but for maths purposes we usually assume that 1 is the first natural number, it's the first counting number. 0 was invented after these numbers. So an example of a geometric sequence could be, there you go, very common one, where what we're doing, we're not adding a constant each time, we're multiplying by a constant. So in this case we're multiplying by 2. Now for both arithmetic and geometric sequences, we worked out how to derive the nth term. I'm not going to rewrite these definitions here, I'm hoping they're starting to become familiar to you. So if you're not sure what they are, go and look them up. But the nth term means it's just a way to generate the nth term in the sequence. So this is called the first one, this is called the second one, and so on. So it's a way, without going through the whole of the sequence, where you can generate the nth term. And we just have formulae for both arithmetic and geometric. Okay, so that was pretty much sequences. So what was a series? So series are related to sequences in that we just add them up, right? So it's the sum of a sequence. And again, there is not consistent the language used. Some people will say the series is the sum of the whole sequence. So in the two cases we've got there, again, we can have the series of an arithmetic or a geometric one. And as I say, some definitions will say it's the sum of the whole series, the whole sequence, I apologise, geometric. So in this case we've got something like this, and we carry on. And in here we're just adding it. And again, you've got formulae that you can use to work these out. So usually what we have is we have to sum the first n terms. Okay, so we usually have a series where we'll have the first n terms, and they are the formulae we've got. So we've got formulae for the first n terms. Now it seems that exam questions, I'm going to say for adding first n terms, obviously first n terms. Now I think here it should say the first n terms of a series, of a sequence. See, I'm getting myself confused. Because the sequence is the one with the individual numbers. So if you add up the first n terms of the sequence, then I think that's what you're doing. Some exam questions often refer to adding the first n terms of a series. But there we go. I think if you're only going to say add the first 4 terms here, what you've done is a partial sum. Okay, so a partial sum is when we only add a subset of a sequence. Now, just interestingly thinking to myself, I think this should be a consecutive subset, so it should be n, n plus 1, n plus 2, and so on. They must be next to each other. You can't say add every third one, and it could be called a partial sum. Add a subset of a sequence. Maybe it's not a subset, it's a subsequence. There we go. I like that better. A subsequence. So part of a sequence. Right, so that's about all we covered, except we did talk about the sum to infinity. So we talked about that, the sum to infinity, and this is only for geometric series. It doesn't make sense for an arithmetic series, because either you're adding a positive number, in which case this is just going to keep going up to positive infinity, or you're adding a negative number, in which case it's just going to head down to negative infinity. When we get a sum to infinity, it's because the series, so the sum converges, and we can actually put a value on the sum to infinity of a geometric series. And there are certain conditions on this, and our condition is it's a geometric series, and the modulus of the ratio, do you remember the ratio is the thing we're multiplying each term by, so that's the common ratio. And so the sum to infinity, it's got to be geometric, and we've got to have mod r less than 1 so that we're converging. So that's pretty much all the notation we've looked at so far. So what else do we need to look at? Well, we have to understand sigma notation. Now, you may have come across before if you've already done some statistics, and the sigma notation looks, this is the Greek letter sigma, okay? This is the capital for sigma. The small version of it looks, and I obviously don't know how to draw Greek, but it looks like this, and you may come across them in statistics. Okay, we use this small sigma, we use to represent standard deviation in statistics. Okay, so that's where you've come across that before. The standard deviation in statistics is represented by a small sigma, and in statistics we've used capital sigma to describe how to evaluate some of these things. So we use formulae using this capital sigma to show you how to calculate the mean, the standard deviation and the variance of a set of data. So what did that look like? Let's just remind ourselves. If you haven't done it, don't worry, because I'm going to go over it all again. What we saw is we saw something like x bar, okay, and this meant the mean, right? So we've got a set of data points, and we refer to those as x. They're our set of data points. X bar is how we represent, is another way of writing down the mean of x. And what we had is we had the formula, this was our formula, sigma x over n. Okay, so this might remind you what sigma meant. It meant sum. Okay, it's pretty good because it sounds pretty much the same. Sigma sum, well, a bit the same. It's got an s and an m in it. So this meant add up all the data points, so the sum of all the data points we've got, and divide by the number of data points. N is the number of data points, which I'm sure you can see is exactly how we calculate the mean. So if we've got a set of data points, we just add them all up, which is exactly what this is saying, and divide by the number of data points. So what's this got to do with series? Well, we've just said in series what we're doing is we're adding the elements of a sequence. So what we can do is this is the typical thing you will get. You will get this sign sigma, and then you'll get the formula. We put in here the formula for the nth term of a sequence. So let's assume we had 2n. Okay, sigma 2n. So this is saying, let's just have a little think, what sort of sequence have we got? Well, what does the sequence look like? The first term is going to be 2, the second term 4, the third term 6, 4, 8, and so on. So think to yourself, what is this? It's an arithmetic sequence. What two things do you need to describe the sequence? Well, you need to know the first one, which we usually refer to as A, so A equals 2. And in this case, we need D, which is the amount you're adding, and in this case, D equals 2 as well. So in the formulae we've got for the nth term and for the sum, those are the two values you'd want, A equals 2 and D equals 2. But just for the moment, we're not going to do this. We're going to take a look here. So we read this as sigma 2n, or the sum of 2n. But in here, we can tell it exactly where we want it to start. So what we tend to do is, do you know what, I'm just going to change this away from an n, because you'll see why in a moment. This is going to get confusing. I'm going to change this to an r. Okay, makes no difference, it's just a number that's representing it. Okay, sigma 2r. And the reason I'm going to do that is because I'm going to put here the limits. So at the bottom of the sigma, we say what's the first value of r we want. So in the case of the sequence we just wrote down here, where the first number is 2, then r needs to be 1 in order to get that first number. So we say it's the sum from r equals 1 to, well, let's sum the first n terms, because that's what we've got our formula for, sum from 1 to n of 2r. So what that means is we're going to add up what we've got here, 2 plus 4 plus 6 plus all the way up to the nth term. So we put r equals n in here, and the last term will be 2n. Okay, so that is all this means. It's a shorthand way for saying add up all the terms like this, and these are our start and end values. So let's have a little look at a couple of examples. First of all, just have a little look at this one. So I'm going to go again from r equals 1 to n, and in here I'm going to have pretty much the simplest thing possible, the number 1. So think about what that's saying. Is it saying sum all the terms from 1 to n, where each term is just 1? So it sounds a bit funny, there's no mention of r in here. So when r is 1, the first term is just 1, and we're summing. When r is 2, well, it's just the same. When r is 3, it's just the same. So all we've got here, every term is 1, and how many of them have we got? Well, I've got from 1 to n, so I've got n of these. So this is pretty much the simplest one we could look at. This whole answer is just, we're going to add n lots of 1, so we're going to get n. So how about something almost as simple, sum from r equals 1 to n of a, where a is a constant. And in fact, I'll say here, let's get used to it, a is an element of, so this is coming from your set notation when we do sets, and the notation I just showed you on the previous page for the natural numbers. So a is a natural number. So what have we got here? So just have a little think. It's very similar to this. I've got simply a plus plus a. And how many of them have I got? Again, I've got n of them. So this would simply be n a. So some of these things can be very, very simple. I think they expect you to know simply just off the top of your head this one. So r equals 1 to n of r. So just think to yourself, what does this actually mean? Okay, and if you get a question like this, it's usually best just to get a feel for what it actually is by writing out the first few. just to make sure you've understood what's going on. So we put r equals 1 in here, and then we add, because the sigma means add. Put r equals 2. There you go. So now you can see what's happening. Our last term is going to be n. And I hope it's familiar to you now, even if you can't remember the exact formula. I hope you can remember how you do it. You write it out backwards. So you'd have plus 3 plus 2 plus 1. And then you say, look, I've got n terms here. If I think of adding these two together, so I've got n lots of n plus 1. So if I match each pair up, but this is going to be twice as much as I want, because I've written it out backwards as well. So what my answer to this is, I've got half of n times n plus 1. And this should be something that's pretty familiar to you, even from GCSE, how to sum the first n numbers. Right, so let's have a look at a couple of worked examples here, which I happen to have a few. Okay, so let's have a look at this one. Excuse me, I seem to have a bit of a tickly cough. Let me just make that a little bit bigger. Right, so there's, as usual, there's different ways to approach this. Let me just move that up there for you. So we've got to calculate sigma r equals 1 to 20 of 4r plus 1. So I'm going to show you, well, I'll show you one way, and then I'll suggest you could do it a different way, okay? So one way is just to, what I just said, let's just start writing out what this is so we get a feel for it. So straight off up here, well, what's the first term? So we're saying put r is 1 into this, okay? So I've got 4 times 1 plus 1, so we've got 5. So it's 5 plus. So put r equals 2 in here now, and we've got 8 plus 1 is 9. Put r equals 3 in, 12 plus 1. Oh, I do apologise, I've no idea why that popped up, but let's ignore it. Something horrible is probably going to happen to my MacBook now. Right, so this is what we've got. So we could say to ourselves, I know what this is, okay, and the two things I need to know, I've got a standard arithmetic sequence. A, remember, is the first number, so that's 5, and D, the difference, is 4. Okay, and you'll quickly start to recognise these from the formulae that are in here. You'll quickly start to recognise that I'm multiplying r by 4, so I'm basically adding 4 on each time. The formula we've got has, for the first n terms of an arithmetic sequence, has n as the number of items we're going to add up, and so that's 20. And so we can just stick that into the formula we've got for summing an arithmetic sequence. So hopefully you remember that s equals n over 2 times 2a plus n minus 1 d. And again, this is something you can just work out. If you forget this, you can very simply work it out by doing the sequence is a plus d plus a plus 2d, okay, all the way up to, well, this is where our n minus 1d is. Our nth term is going to be a plus, I've run out of space, n minus 1d, and then you play the same trick, you double it up underneath, okay? So underneath here we'll have our last term, a plus n minus 1d, and then each term can line up until under here this is going to line up with a. So again, we've got n terms because they all line up, and each term is 2a plus n minus 1d, what we've got in there. So I've got n lots of 2a plus n minus 1d, but I only want half of it because I only want one of these, not both of them. Okay, just an aside, but I want you to really understand where these come from. They're not magic formulae. Okay, and sometimes you might have to work something out like this yourself, so it's worth remembering it. So you can just go ahead, you can pop these values in here, pop it in the formula, and you should get 860 out of it. Now, as a challenge, I want you to go and read about your calculator, and you will find that your calculator is capable of calculating sums of series. So since it's a bit tricky for me at the moment to demonstrate calculators to you on here, but go away for your calculator and investigate how could you work this out, or at least check your answer, because obviously in the exam you've got to show what you're doing. Check your answer that for the given series this is the sum you expect. Okay, I did say I'd talk about this a slightly different way, and I'm not sure whether this is going to crop up in exam questions. We'll have to see when we start looking at exam questions, but I just want you to think about the fact that what we're doing here, we're adding from 1 to 20 for r plus 1. Okay, I want you to convince yourself that this we could break down into simply, I'm going to add from 1 to 20. If it's obvious, if you've only got one number here, I've only got one number r here, you can omit what the variable is here. It's probably a bit sloppy, but I'm going to do that. I'm going to suggest that you could split that up into two parts to start with. Okay, so we've got this, because really if you think about how I write this out, you should be able to see that I could easily just rearrange all these terms and end up with two separate terms. And then what you could do is simply, it's 4 times the sum from 1 to 20 of r plus the sum from 1 to 20 of 1. And so we've broken it down. Instead of having to remember this formula, we've broken it down into two very simple things which we had on the previous page. Okay, let's flip back up just to prove it. So you need to know the sum from 1 to 20 of r and the sum from 1 to 20 of 1. Well, there you go. The sum from 1 to n of 1 we said was just n, and the sum from 1 to n of r is a half n plus 1. So you could, and do this as an exercise, just pop those definitions into here and check you come out with the same answer. Okay, so this can be a handy thing to do if you're just struggling to remember, have you got this exactly right? Okay, so that was the first example where we were summing an arithmetic sequence. So let's have a little look at a geometric sequence. What have we got here? Okay, so I haven't yet worked out how to get this to come onto the board in the exact size I want, but never mind. Okay, so here, find the values of the sum from k equals 1 to 12 of 5 times 3 to the k minus 1. Okay, so let's look at this one first of all. So let's get a feel for it. So this one equals, right, substitute k equals 1 into here. What is that first term going to be? Okay, so as an aside, we've got 5 times 3 to the 0. Okay, please, 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 if you're not absolutely convinced what 3 to the 0 is, go back and revise your indices work, because this should be something that is just very familiar to you. 3 to the 0 is 1. So our first term is 5. Our second term is 5 times 3 to the, well, now k is going to be 2, so 5 times 3 to the power of 1. So 5 times 3, 15. Getting the hang of it. Our third term, put k equals 3 into here. So this term becomes 3 to the 2. 3 to the power of 2 is 9, times 5 is 45. OK. So can you see now that we've got a geometric series here? So for a geometric series, what you want to be looking out for is this sort of thing, 3, or a number to the power of what you're indexing over, and then you're probably going to have a geometric series. So once again, we know the formula for the sum of the first n numbers, so in this case n is going to be 12. What else do we need to define a geometric sequence? We need a, the first term, so in this case we've got 5, and we need r, the common ratio. So what's the common ratio? What are we multiplying by each time? We're multiplying by 3. Okay, and we can just pop those into the formula. So if you remember the formula for the first n terms of a geometric sequence, and just to remind you about this notation, okay, Sn, so that's another way to write the first n terms, is a times r to the n minus 1 over r minus 1. Now you'll recall hopefully that there's 2 different versions of this. The other version is a times 1 minus r to the n over 1 minus r, and they're both equivalent, but it's usually just helpful to choose the one that's going to make you divide by a positive number. So in this case r is 3, so this is going to be much nicer, this is going to be 2. And then we just plug everything in, so I'm going to leave that as an exercise for you to check. You can use your calculator, plug those values in, and you should come up with 1328600. Okay, so that's the answer to part A. So B, let's have a look. On the face of it, looks pretty similar. I've got the sum. I've got 5 times 3 to the k minus 1. So exactly the same, right? Our terms are exactly the same. We're looking at this sort of thing. So what's different? What's different here is that we're not starting at k equals 1, right? We're starting at k equals 5, and we're going up to k equals 12. Now again, there's a couple of strategies you can use for this. So given we've already calculated this, the easiest strategy is to think, well, okay, I want to add the terms from k equals 5 to k equals 12. So let's just think over here. I've got a typical sequence. I've started at u1. Okay, so let's think about this. I've got this sequence here, sorry, this series. So I'm adding up n terms. But I only want to add up here, I want to add up, let's actually put 12 in, should we? Let's put 12 there. I don't want to start from that, I want to start from the 5th term. So I'm not starting from k equals 1, I'm starting from k equals 5. So I only want u5 plus u6 plus up to u12. Right, so looking at this, I'm hoping you can see that what I could do, I've already got this one, I know what this whole thing is, I just need to take away the first few terms. So I'm going to rewrite this and hope you can see this. So I've got exactly the same thing in here. So we're going to go, this time I'm going to do the whole thing, right? So I'm going to go from k equals 1 to 12. The whole thing, that's what we've got here, and then I'm going to subtract k equals 1 to 4, right? So I'm going to take the whole thing and then take away those elements at the front that I don't want. So that's the first 4 elements. So all I have to do is to work out this, okay? And so for this term, well, what have we got? We've got, is that almost the same things here. We've got a equals 5, r equals 3, but this time we've just got n equals 4. So straight away I can put this whole thing is 1328600 minus, and we'll just pop those values into here. So let's just do this together. We're going to have 5, that's a, times 3 to the 4, so r to the power of n minus 1 over 3 minus 1. So that's what you're going to pop into your calculator, and hopefully you should come up with the answer of 1328400. Right, so this is often the easiest way to do things. I'm just going to suggest to you there is an alternative strategy that you could use if you want. So where am I going to go? I'm just going to partition this off, okay? It's going to look a bit messy, but hey. Right, so let's think about what this would look like. What's the first term going to be here? Well, I'm going to put k equals 5 in. So my first term is 5 times 3 to the power of 4. Okay, so that's my first term. And then we're going to carry on. And it's going to be just the same. What we're doing is still multiplying by 3 each time. So my second term is 5 times 3 to the power of 5, and so on. Okay, so we're going to add all those up, and we're going to go up to when k equals 12. So my last term is going to be 5 times 3 to the power of 11. So what you could do is you could say, well, what have I got here? I've got a geometric sequence, but this time a, my first value, is 5 times 3 to the 4. R is 3, and n is the number of terms. So this is where you've got to be very careful. How many terms have I got here? And sometimes it's very tempting to just say I've got 12 minus 5. I've got 7 terms. But you have to be really careful. We've actually got 8 terms, okay? And the way to convince yourself, if you're just at all doubtful about what's going on there, is to think, if it was k equals 5 to 6, how many terms would I have? Well, I'd put k in as 5 and I'd put k in as 6. I'd have 2 terms. So when this is a 6, I'd have 2 terms. So it's not as simple as 6 minus 5, okay? You have to be very careful. So it's 12 minus 5 gives us 7, but then I've got the extra 1. In fact, it's almost like an extra 1. So I've got n equals 8. Okay, so I could then just put those values into my formula here. And as you're using a calculator, really is the just what you could do. There's another way you could think of this. There's always lots of alternatives in maths, and sometimes it's going to be useful to be able to be a bit flexible in your thinking. Instead of saying, look, this whole thing is my first term, and I'm multiplying by 3 each time. Actually, no, ignore me. I was thinking of something slightly different. Okay, so you could just do that and stick it into the formula, and that would give you the correct result here. So it might be worth you just trying that out to check that you do get exactly the same result. Okay, and then you've obviously got a bit of flexibility. Now I was going to do, let's do this. Let's work through an exam type question for you to see what this is, and then we're just going to do one more thing after this, I think. Here we go. The problem with the way I'm recording this is I have absolutely no idea how long I've taken so far. So here's our question. Okay, so it's a bit more, I was going to say convoluted. There's obviously something more to it. They're giving us the solution to what this partial sum is, and then they're asking us to show that this thing is true about k. So these are really great questions for you to tackle, because you know that if you can massage this into this formula, then you've got it right. You must have done this first bit right. And even if you don't get to that, then as long as you understand what's going on, you can carry on. Even if you don't get there, you can assume this and carry on and do the second bit of the question. Okay, so I believe there were 3 marks for this first bit and 2 marks for the second bit. So even if you goof on this first part, you can still go ahead and get 2 marks for the second part. So let's have a little look. I'm hoping you can start to recognise now that this, so we're multiplying the index, and here the index is, they're saying from R equals 1 to K. So R is our index, K is the number we've got. So we're multiplying R by 3 each time, so we've got an arithmetic sequence. So what have we got? Let's go. And a good way to do this is to say left hand side, right? So the left hand side of what we have got here is, let's just look at this. We've got R equals 1 to K of 8 plus 3R. Now if you can recognise that's an arithmetic sequence, then you can simply work out what do we need. We need to know A, D and N. Okay, so if we look at this, A is the value of the first term, so we just have to pop R equals 1 in here. So A is 11. D is the difference, so the common difference, what we're adding on each time. D equals 3, and N is the number of terms, so N equals K. Okay, so this is saying it's probably, if you're going to do it this way, it's probably worth saying arithmetic. It's an arithmetic series or sequence. I really don't think it matters which you say here. So then you've got the formula. So the left hand side equals, and we'll just plug this in. So we've got it's n over 2 times 2a plus n minus 1d. So here we're showing we know the formula for the first n terms, and we'll plug those values in, okay? So let's be careful. What's n? N is k. Okay, so we've got k over 2 times 2 lots of a's, 22, plus, again, we've got k, so instead of n we write k minus 1, and d. Well, d is 3, so I'm just going to pop that in the front, because that's just the normal way to do it. It's just going to make it possibly slightly easier. So at this point we could leave it like that, or what we could do is I'm going to leave the half, okay, because I don't need to evaluate it, and let's just work this out. We've got 22k from that bit. I'm going to get rid of the brackets and multiply by the same thing, so plus 3k squared, okay, so 3k times k, and here I've got minus 3 times k. So I can just tidy that up. So I've got a half of 19k plus 3k squared. Okay, so we're given a half times 19k plus 3k squared equals 377. So I really don't think at A level you need to do this, but do you know what? It's not a bad habit to get into to show exactly what you're doing. I'm going to multiply both sides by 2 to get rid of a half. If nothing else, it's reminding you when you come back to review your question in an exam, it's showing you exactly what you did. And this is going to be much more helpful in you quickly reviewing, have you got it right, or spotting silly errors. So what I'm going to do here is I'm going to rearrange this, and I'm going to say 3k squared plus 19k, just because that's normally how we write. We normally do the squared terms first and come lower in order. Equals, I'm hoping you can work out 2 times 377, but don't worry, you have got your calculator. So this is 754. So bearing in mind what we want to get to, right, it's looking good. We've got a quadratic So we've got this is our normal way of solving a quadratic equation, and it's looking, we have got a quadratic equation, so just follow the steps. So we'd have 3k squared plus 19k minus 754 equals 0. Now I don't know about you, but if I got this, I'm probably not going to start trying to find my factors of this and then trying to work out what's going to give me 19 when I multiply it by 3. I'd probably go for doing something different at this point, and it would all come out in the wash. So probably use the quadratic formula and notice that the square root just came out nicely. But I don't need to, because look, they've shown me what I'm hoping it's going to end up as. So all I need to do is check. So I need to check 58 times 13. So I can just show this. If I've got a calculator, I just pop it in. Is 754. So I could say something like this now: 58 times 13 is 754, and then whatever your favourite method of factorising this would be. I know some of you would split this. It's not an approach I like to take, because I think you very rarely need to do that. I would just say, well look, I know it's going to go into two brackets. I mean, for heaven's sake, I know what it's going to be, right? So I want to get to 19, and I know I've got my factors 58 and 13, so it's just a case of which way round they go. And they've told us, essentially, it's now it's debatable at this point as to how much you need to say. You could just go from here to here. I'd be inclined to say, because, now this is interesting, I don't know if you've come across this, you've probably come across this one meaning that, oh, this one means therefore. I'm sure you've come across this. If you turn it upside down, it's shorthand in maths for saying because. I don't think it's actually something you need to know for A level, but I find it really useful, and you might notice that I do this. So this is true because 58 take away 3 times 13. Oh, I missed the 8. How did I do that? So I've got 58k, take away 13, take away 3 times 13. So 58, take away 39 is 19. So I think this is sufficient for you to prove that this is what you've got. So hey ho, you've got to here, you followed through, and you know you've just got 3 marks. Find the value of k. Okay, so normally in a quadratic, what would you do? You say, I've got two things multiplied together by 0, so either this is 0 or this is 0. Okay, so you can do that, but it says the value of k. So let's think about it. When we see an expression like this, r equals 1 to k, we know k equals, k has got to be one of the natural numbers. So you could say, as k is an element of n, or you could just say k must be a whole positive number, or k must be a counting number, whatever, however you want to say that you know k is restricted, then k equals 13 is the only solution. Okay, so something like that. So that's the sort of thing you might get in an exam question, and I think they're always great ones to go for when you get a show that. Right, the next bit is fairly easy, so we will move on to it, although we spent quite a long time on that. So let's have a little look. Right back at the beginning, on the very first thing when we looked at sequences, we looked at arithmetic sequence, we looked at geometric sequences, and just because I always love to remind people, we looked at the Fibonacci sequence. And we said this is neither arithmetic nor geometric. Quick reminder, you really should know this by now. Okay. This is defined by, to get the next term, you add up the previous two terms. Okay, and I said at the time, so this is defined as a recurrence relation. So the nth term, if we think about it, well, let's just think of a couple of examples. How do I get, say, the 5th term? So u5. That's got from, well, I add the previous two terms, u4 plus u3. So let's think about it. Un, the nth term, is defined as, Well, it's the one just before, so that's going to be the n minus 1th term, plus, and the one just before that, so that's going to be un minus 2. So this is how we can describe Fibonacci, that's how to get the nth term. So this is a recurrence relation. So to get the next term, it depends on some of the previous terms, okay? That's what it means. So the next term is defined in terms of the previous term. So the next term defined by previous terms. Now, it depends how far back you have to go. So for Fibonacci, we have to go back 2 previous terms. So sometimes we describe this as a second order recurrence relation, or I think I've seen it, a recurrence relation to 2 degrees. So there's different terms. But for A level, you only have to know if you're going back 1 term, okay? So a recurrence relation for A level, Edexcel A level, you have to know something, and they define it in terms of un plus 1. So how to get the next term if you know the first n. So they say un plus 1 is a function, and this could be anything. It's a function of un, the previous term. So this is all you need to know about, which makes it somewhat easier. So there's almost nothing new here. So shall we just look at an example? Let's see what I've got. Here we go. Right, so here we have 2 sequences defined. So what have we got here? So un plus 1 equals un plus 4. Now obviously it's just like we should have thought about this. So I know how to get from one term to the next, but how do I define the sequence? What do I need to define this sequence? Well, I need to know the first term, don't I? I need to know what u1 is, right? I need to know, once I've got the starting point, then I can then calculate every other term from there. So it's just like when we were looking at arithmetic and geometric ones, we said what do we need to know to define the sequence, and the starting value is always one of those things. So here you can see we've got un plus 1 equals un plus 4, and we're starting with u1 equals 7. So all we've got to do is start to write what the terms are. So we've got u1 equals 7, u2 equals, we've just got to pop it in here, 7 plus 4 equals 11. u3, well, I don't need to worry about anything, I just need to pop the previous one into my formula. So it's u3 is u2, 11 plus 4 equals 15. Okay, and u4, well, all I need to know here is u4 equals u3 plus 4, so 15 plus 4 equals 19. So you can see here, so what sort of sequence have we got? We're just adding 4 on each time. So we could define this as an arithmetic sequence, and A would be 1 and D would be 4. So this is just a different way to define an arithmetic sequence. So let's have a look at this one. Well, what's happened here? We've got un plus 1 equals un plus 4 again, exactly the same. But in this case, we've got u1 equals 5. Okay, so we've got a different starting point. And here, we're just going to get 5 and then 9, 13 and 17. Okay, so it's usually very simple just to pop those terms, pop your first value in, and then it's a bit like when we've done iteration, you're just taking a value and doing the same, reapplying the same function over and over. So if you've done iteration, this is probably going to be familiar to you. So what can we do with this? Because obviously they're not just going to give you questions like this, they're going to expect you to do something a bit more. So I have another example here. Let's have a look. this. So here we go. So they're not telling you, they're just saying this is how it's defined. So you've got to think to yourself, whoa, okay, so I've got, this is a recurrence relation. So what have they told me? The first value here, A1, is P. So it's a bit unusual, we haven't got an actual number here. And then they've told me to get the next value, to get an plus 1, I've got to do an squared minus 1. And this is true for n greater than or equal to 1. Okay, so we've got, let's have a little, so first thing we've got to show what A3 is. Okay, so we know A1 is 1. Sorry, A1 is P. And we're just going to pop this in. So that's all we can do. We've only got to get to A3, so we've got A2 is, well, let's put it in first. We've got A2 is A1 squared. I'm just showing I know exactly what's going on here. Okay, A2 is A1 squared minus 1. And now I can pop in the value for A1. So A1 is P. So here, A2 is P squared minus 1. Okay, so A3. So again, let's show exactly what we're doing. A3 is, going back to the formula here, A3 is A2 squared minus 1 equals, well, what's A2? A2 is P squared minus 1. P squared minus 1 squared minus 1. And then they've shown you what format you need to get this in, right? So another great question, because it's a show that, we'll know if we've got it right. We just have to expand this out. So you should know how to expand terms like this quite easily. I hope you should be starting to do this in your head now. I'm going to have square of this term, so p to the 4th, minus twice the square, excuse me, 2 lots of this times this, so I've got minus 2p squared, and then I've got plus the square of this term. So plus 1, and then my minus 1 here. So I've got p to the 4th minus 2p squared. So that's what they asked us to show, what A3 was. Okay, and then part B, so this is part A. Part B. So given that A2 equals 0, we've got to find the value of, oh gosh, I've written that in the wrong place, haven't I? The magic of undo. A2 equals 0. So A2 equals 0. So here's another symbol. Have you come across that? That just means implies. Maths is great when you learn to use all these symbols. So A2 equals 0 implies that, well, A2 is p squared minus 1. P squared minus 1 equals 0. Okay, so how are you going to solve this? Well, it's pretty obvious, isn't it? You've got p squared equals 1. So I'm going to square root each side, so p equals plus or minus 1. Right, so at this point we've always got to think, well, there's several clues that make you, well, at least one clue that makes you think, is it 2 possible solutions? And one is, in the question, they say the value of p. So this is implying that there's only one value of p. So why are both of these not valid? Well, we look back here, we've got p is less than 0. Okay? So we are given p is less than 0, so p equals 1. So p equals minus 1. Okay? So that's the answer to part B. So C, we've got to find r equals 1, so the sum from r equals 1 to 200 of a r. Right, so at the moment it's a bit hard to see what's going on here. So let's start writing them out and see what's going on. Okay, so we've now got, we put P, sorry, we've got, so let's see what this is. So we've got P equals -1. Do you know what? It's not that obvious that this follows on from here. You've got to assume here P equals -1. Right, so our sequences, so we've got, let's have a little look. It's not obvious what's going on, so let's see. So A1 equals P. A2 equals this squared -1. So square this, -1 squared, we could write all this down here. -1 squared -1 equals 0. A3 equals 0 squared -1 equals -1. Oh, now you should notice something here. We're in a recurrence relationship. So once you get the same number back again, you're just going to keep performing the same thing, because I'm just going back to the previous term. So this is 0. So I haven't introduced the name of this sort of sequence yet. So this is, we're going -1 0 -1 0 -1 0, and something like this that repeats. So I've got this repeating pattern over and over. This is called periodic. So that's one of the last few little things we've got to cover, but I don't intend to do that today. So this is periodic. So yeah, sorry, just my brain was just going. It's periodic sequence. Right. So let's think about this. We've got to add up the first 200 terms. So I'm going to have, if I think about this, so in the first 200 terms of AR, there will be, so it will have 200 times -1 terms and 200 times 0 terms. Okay, do you agree? I'm alternating, so I'm going to have 100 of each. For heaven's sake, I think we've done enough now, because my brain's gone. I'm going to rub that out. We've got 100 of each, so it's going to be, so that sum will equal, well, all we're going to have is -100. Okay, and finally we'll do that very last little bit. Write down the value of A199. Write down. That means you don't have to do any calculations. You just got to write the value down. So I'm going to go up here. I must learn to be less messy. So A199, what does it mean? It just means the 199th term. So we can see, if we look here, what do we know? All our even terms are odd. So all even terms are odd. All even terms are 0. I need a cup of coffee. And odd terms are -1. So A199, well, it's an odd term, so we can say A199 equals -1. Right, hopefully that all made sense. I will give you some questions to do on a worksheet. And this is just really building on the stuff we've been doing in the past 2 weeks. So there you go. Have fun trying questions. And I won't give you many because that was hurting my brain. So there you go. Enough for today. See you next week. Bye.